right, guys, welcome to JMU, one of your favorite group classrooms, right outside my office. So hopefully this room will work well. There's a lot of light back here, so we'll just see how this all works on this particular whiteboard, even though I'm not a whiteboard fan. So let's just go with it. So here is section 1.2 without delay, slope fields, okay? So remember, chapter 1, which is where we are now, is about first order ODEs. Okay, first order ODEs. That's our chapter 1. And for first order ODEs, the most general form is some function of, if we have a first order ODE, and if we say for a dependent variable y as a function of an independent variable x, we've talked a lot about those guys, then the most general form is g of x, the independent variable y, the dependent variable in the first derivative, y prime, is equal to 0, right? And if we can solve that equation for y prime, then we are in a nice format for dealing with slope fields. So if we solve that guy as y prime is some function of x and y, then we have exactly what the name says. What is y prime? This is the slope, right, of what? Good. The tangent line to the graph of the function y, right, the graph of y, at each x, right, for each x in the domain, right? Slope of the tangent line to the graph. And so that's what this guy is, right? And what's a field? Well, a field, there's a lot of ways to talk about a field, right? Not one that we want to run nicely through the grassy green field. But here the idea of a field is some function that has some value at each x and y. So you can think about this board, right, as a piece of a Cartesian plane. It has an x direction and a y direction, and maybe at each point on this board we talk about whether or not we have writing on it. Okay, so that would be some idea of a field. Or you could talk about a stovetop as a Cartesian plane, an XY coordinate system, and if the burners are turned on, then at each XY there is some temperature associated with that flat surface, that stovetop, and the temperature would be a temperature field on each XY, right? So that's kind of the idea here. This is a function that has some value at each point in the Cartesian plane, right? And what value is it going to have? Well, it's going to have the value of the slope of the tangent line to the graph of a function at each x. And so that's the whole point of slope fields. We are going to look at a visual way, a visual approach, a visual approach to seeing DEs and their solutions before we start actually solving them with mathematics. Okay, so no DE solutions right now. We're just going to try to start understanding them graphically and visually before we dive into solving them. Okay, so this guy under nice conditions can be put into this form, and if we've got this form, then we've got the derivative, the first derivative isolated, and it equals some function of only x and y, right? So for example, let's look at, let's look at an equation like this. Let's say x cubed y to the 7th plus sine of y prime minus the square root of y e to the x cubed y is equal to 0. Okay? So here is a nice, what kind of differential equation? You should be running off all of those words right now, right? Okay, are we good? First order, right? It's nonlinear for multiple reasons, yeah? It is not autonomous, right? Okay, okay, so here's a differential equation, and this guy, right, would kind of be the g of x, y, and y prime, right? That's what this guy would be, this side, yeah? Okay, and for those of you who are like worried about, we could say plus 5, right? Okay, so that's the whole idea of equal to a 0 versus equal to a constant versus equal to some function of x, right? You could always bring it across, yeah? Okay, so here is an ugly first order differential equation, yeah? And for nice values, we could solve this as y prime is equal to. So if we solve this, right, we would have our sine y, right? And we bring everything across the other side, so square root y e to the x cubed y minus 5. And then this guy across, minus x cubed y to the 7th, right? And then what do we want to do, right? We want to divide by sine y. Something should be going off in your head right there. And now it has this form, right? So we went from this form, yeah, g of x, y, and y prime equals 0, to this form, y prime is some function of x and y, yeah? Okay, does that make sense? So this would be our g of x, y, and y prime, and this guy is our f of x and y. Okay, now this isn't going to be an equation we're going to do much with because it's pretty ugly. And, but let's talk about this guy. Okay, well, you should have been a little bit cringy when you divided by sine y, right? Because we know we cannot divide by 0, yeah? Okay? And so already we see an issue going on with this equation that writing it in this form is problematic anytime sine of y is 0, right? Okay? So if we think about that, and think about the xy plane, yeah, which we labeled, okay? Then for values of when is sine of y 0? Well, let's think of just a couple, right? So when y equals 0, sine of 0 is 0, right? So if y is 0, we can't let that guy in, like he's not allowed. And if we have y as pi, right? So if this is pi, right? This is the y-axis and that's pi, right? Then, you know, we would want to avoid that as well, right? And so for this problem, right, this guy is making sense if y is kind of like in this region here between 0 and pi, or maybe pi to pi over 2, right? Or, you know, 0 to negative pi, yeah? Okay? Not including those endpoints. Okay, so here we solve this guy explicitly for y prime equals this stuff, right? Now, if this was sine y prime or square root y prime or e to the x cubed y prime, good luck solving this for y prime equals f of x y explicitly, okay? So, so anyway, right, we are interested in what to do with an equation that looks like this, okay? Visually. Now this one is too ugly for us to jump off with, so we'll just take a look at something a little bit nicer, because one of the things we've been doing is remembering some calculus, right? So remembering some derivative rules, we've been remembering some integration rules, and now we want to see a variety of ways that calculus can help us understand equations like this that maybe, you know, aren't quite as ugly as that one. I just want to make sure you're awake to get us started, okay? Another thing about your book, just ignore, whenever the book is switching x and y's from pages 23 to 24, ignore that for right now. And also ignore example 1.2.3. Also, you can just skip over that one in your book, okay? All right, so before we get started, we want to talk a little bit about this idea of when we're going to have a solution of an initial value problem, right? So this guy is our ODE, right? If we're gonna have an initial value problem, then we need to add an initial condition, right? And then we've got our IVP, right? Yes, we're good at these letters now, yes? We're super good at these letters. Okay, so that's our ODE. What's our initial condition gonna be, right? Let me get that. So our initial condition is going to be, what's our classic initial condition or generic one? Y evaluated at some initial value x naught is some given constant initial value y naught, right? The point x naught, y naught is on the graph of the solution, yeah? Okay, so let's start with a theorem, right? Okay, so here's our theorem, okay? And this is Picard's theorem. And what's it about? Existence and uniqueness. Existence and uniqueness of solutions of an initial value problem, okay? Solution to an IVP, okay? So when we're solving a problem like this, you certainly want to know there is a solution. That's existence, right? You want to know there is one. Otherwise, you're going to spend a whole bunch of time trying to find something that doesn't even exist, and that's going to be kind of futile, right? But you also want to know when the solution is unique as well, right? You want to know that if you found one, that that's it. It's the only one. There's no other one out there, right? Okay? You know, you don't want to know, you don't want to find one and then be like, well, how do I know there's not like 47 more, right? Okay? So this theorems on existence and uniqueness are awesome because then you know if you find one, it's the only one, right? Okay. And sometimes you can't even find it, you just need to know it's unique. And sometimes you just need to know you have one. And you don't care if it's unique, you just want to know there is one, okay? So, well, we've got existence and uniqueness, so we're going to get both with this theorem. So what does it say, okay? So let's consider our IVP, okay? So consider the IVP that we have written right here, okay? Given. So I won't rewrite it, here it is, okay? Then what does it say? The theorem says if, right? So here's the hypothesis coming. If my function there on the right-hand side, f of x and y, right? If that guy is continuous, one of our fun calculus words, right? Woohoo! We love calculus words. Is continuous, right? And if the partial derivative, we talked about those guys, of f with respect to y, we'll do some examples in just a minute, so don't freak out. If the partial derivative of f with respect to y exists, so if we can take that derivative and there's some function, okay, and that function is also continuous, okay, exists and is continuous. Well, we can't like expect like everywhere, right? That's asking a little bit too much. So for right now, we're just going to say near the initial value, x naught, y naught. We'll say what we mean there in just a little bit, okay? So let's draw a picture here for a sec again. Here's our x-axis, here's our y-axis, yeah? And so, you know, maybe this value right here is x naught, and maybe this value right here is y naught, and so we want a solution of the differential equation that goes through the point x naught, y naught, right? Okay? Alrighty, and so let's finish writing this, then we'll talk about what these guys mean. Okay, so if I have continuity of that right-hand side function and its first partial with respect to y, then what do I have? Then we can do a little math. fund. What does this mean? What does that mean? Anybody know? Right? This is mathematician shorthand for there exists a unique, right? There exists a unique, yeah? There exists a unique, backwards, uppercase E, exclamation point, unique, right? We say this all the time. Another way to say that, also known as, then there exists a unique what? Solution to the IVP nearby X naught at least. So we'll talk a little bit about what those mean as well, okay? Nearby X naught at least. Another way to say this, there exists unique solutions of the IVP is that there is one, so one exists, and only one, not more than one. There is one and only one solution to the IVP. Near. That's not why not. Okay, so what does all of this mean? Visually, you might think about it this way. Okay. Visually, what do we need? We need continuity. This is a function of two variables, right? So it has to be continuous in both x and y, near x naught and y naught. So I have to be able to go some distance away from y naught and some distance away from x naught, and be guaranteed that for all x's in this interval, that function and its first partial are continuous functions, and that for all y's in this interval, that function and its first partial are continuous, right? So what does that really do? It sets up kind of a rectangle, right? A rectangle of space, right? In the xy plane, where within this rectangle in here, we have continuity in x and y for those two guys. So for all of these xy's, right? Okay. And then what does this mean, right? So we could say, right, we could call this guy here, right? We could call this distance, say, A. We'd like this distance to be symmetric. So this would be x naught plus A, right? So that this is A, then this over here would be, good, x naught minus A, yeah? Okay? And basically we could say that x could roam as far away from x naught as A. How do we say that in math? Calc 1, nice absolute values. The absolute value of x minus x naught is less than A. X can roam at most A units away from x naught. The distance between x and x naught is smaller than A, right? So what would it be up here if we called this distance here B, right? Then this value right here is y naught plus B. This is y naught minus B, yeah? Okay, and then these y being allowed to range from there to there is the same as saying the absolute value of, you got it, y minus y naught is less than B. Very nice. The distance between y and y naught can be no bigger than B, yeah? Okay, well then what does nearby x naught at least mean, right? Well, it means there exists some number, let's just call it h, such that the solution is unique. What is the solution? The solution is y is a function of x, right? Because it's a differential equation, and y is our dependent variable and x is our independent variable, right? So there exists an h such that the solution y of x is unique. Ooh, this is not such a great red marker. Is unique for what? Well, x ranging away from x naught by at most some number h. You don't know what h is, okay? Yeah, okay? H exists, so I can go, the solution will exist nearby x naught, right? Does that make sense? Okay? All right, we'll look at some examples here, but that's the nitty-gritty of the theorem. Okay, so what matters? Continuity of this guy and its partial derivative with respect to the dependent variable, right? Those guys have to have continuity, right? And what is continuity? Remember that. When do you not have continuity in calculus? Like when you're dividing by 0, right? When you're taking the natural log of 0, right? When you're putting in some value into a function that makes it not exist, right? Yeah? Okay? All right. So all those fun continuity rules we love from Calculus 1, yes? Okay, so let's look at a little more terminology before we keep going with this. Now, some of this terminology is not in your book. So what we're going to do right now is kind of add on to what's in there so that we can have a more robust understanding of what's happening from our calculus skills, right? And that's what we're bringing to the table. What's what we brought with us here is calculus skills. Yeah? Yeah, I know. I'm smiling too while you're smiling. All right, let's look at some more terminology. I promise we're going to get to some concrete examples, okay? But let's hold on. More terminology. So here's one thing. We want to be able to talk about an equilibrium solution. Okay? So what is an equilibrium solution? An equilibrium solution of the differential equation y prime equals f of x and y, okay, is a solution. Right, well, let's see, what do you think? What does equilibrium mean, right? It means not changing, right? Right? If the solution's not changing, right, then what do we know from calculus, right? Its derivative should be, you got it, 0, right? Okay? And if it's a solution, it's got to be y equals something, right? Because our solutions of this differential equation, y is the dependent variable, yeah? And so it has to be y equals something. So if it satisfies y prime is 0, and it's y equals something, it's y equals a what? Good, a constant. Very nice. An equilibrium solution of y prime equals f of x, y is a solution y equals some constant. Such that y prime is 0. Right? Okay? So, what do we do? Right? Well, if y prime is going to be 0, that means we're looking for this right-hand side to be 0. So we're looking for values of y equal to a constant that make this guy equal to 0. Those will be called equilibrium solutions. Okay, what else? Let's look at an example. Okay. Let's look at the ODEs in problem 1.2.6. Okay. You're gonna have to hold on for a sec. So in 1.2.6, we've got these two ODEs. Well, I think there might be more, but let's just write these down. This is what I have written down. One of them is y prime is equal to 1 minus x, okay? And the other is y prime is equal to x minus 2y. Okay, so let me ask you this. Do either of these two ODEs have an equilibrium solution? What do you think? Well, what's our definition right there? Well, if y prime is 0, that would mean setting this equal to 0. Is that going to result in y as a constant? No. So there are no equilibrium solutions. Yeah? write that. Yeah? What about this guy? Well, if y prime is 0, well, that would imply x minus 2y is equal to 0, right? Which means x is 2y, which means y is 1/2 x. Yeah? Is that an equilibrium solution? No. Good, right? Not an equilibrium solution, right? Why? Because what? It's not y equals a constant. Okay? This is a line across which the slope of the tangent line to the solution is 0, right? Good. Why? Y prime is 0, right? Okay. So what do we have there then? Horizontal tangent across that line. Yeah? So let's look at some examples. Now this one, you can solve. This is 1.1 methods, right? Why? Because we have y prime, y is our dependent variable, x is our independent variable. This right hand side is only a function of x, you're just integrating. This is just a calculus problem. Find me all functions whose derivative is 1 minus x, right? Okay? This one, find me all functions whose derivative is its independent variable minus 2 times itself. That one is not 1.1 methods. You can't just integrate both sides because you got a y over here, yeah? So we're gonna need some other method to solve that, right? This is coming up very soon. What kind of an equation is this? It is a first order. I hear it. Linear, non-autonomous, non-homogeneous. Bring this guy across, right? Left with the x over there. Constant coefficient. Very nice. ODE. Yes? Are we good? Awesome. Okay. So, that guy is coming up. Stay tuned for more video lectures. In order to solve this, but we don't have to be able to solve it to understand what its solutions look like. And that's what section 1.2 is about, okay? Does that make sense? And that's what we're gonna do right now, okay? So, let's take a look at this one, okay? So, and we're gonna try to look at its slope field, okay? So what is happening here? Let's draw an XY plane, right? And we do know, right, if we do set y prime equal to 0, right, that says that, well, 1 is equal to x, right? So if y prime is 0, x is 1. Well, what is the line x equals 1, right? That is this line right here, right? The vertical line x equals 1. So what do we know? Well, just like over there, what happens? Along the line x equals 1, the slope of the tangent line to the solution is 0. So we have horizontal tangents, right? Horizontal tangents across this. So what we're doing in drawing a slope field is putting a little line, a little slope, right? Anytime a solution touches x equals 1, it has to cross with a horizontal tangent. Does that make sense? That gives us some information, right? Okay. So we know that much. Well, what else do we do in calculus? We think about, well, where is y prime positive, which means y is what? Y prime positive? Y is increasing, right? And y prime negative, y is decreasing, right? So if I think now about splitting this up into, well, what about y prime positive? Well, y prime positive would mean 1 minus x is positive, right? Which would mean 1 is greater than x. So x is less than 1, yeah? X is less than 1. So for x less than 1, what do I know? Y prime positive, that also means, what do I know? Y is increasing. Yeah? So over here, my solutions increase. Let me grab a couple of them. So over here, right, we've got increasing. I'll just write it. Right? If x is less than 1, solutions increase. Yeah? And then, if y prime is negative, well, what would that mean? 1 minus x is less than 0. So adding x to both sides, x is greater than 1, right? If y prime is negative, what does that mean about y from calculus? Y is decreasing. So y is decreasing when x is greater than 1, and y is increasing when x is less than 1. So over here, our solutions are decreasing. Yeah? Okay. What else can we look at here? Y prime. We've talked about there are no equilibrium solutions. We found out from calculus where solutions are increasing, where solutions are decreasing. What do you do after talking about increasing and decreasing in calculus? Yep, indeed, right? You look at the second derivative. Now for this problem, the second derivative is relatively simple, right? What is the second derivative? If y prime is 1 minus x, because we only have x's over here, this is a relatively simple calculation. If y prime is 1 minus x, what is y double prime? Derivative is, good, negative 1. Yeah? Okay. Well, what do we care about with y double prime? What does that tell us about? Good, concavity. What do we know about negative 1? It's always negative. So if the second derivative is always negative, then what does that mean about y? Y is concave down everywhere. Yeah? Everywhere. So the solutions, you probably guessed this a while ago, but it's fun to think about it in this different way, right? Instead of just integrating and coming up with a solution, what do we have? We have a visual representation. Solutions increase over here, they decrease over here, and solutions are always concave down, right? And across here, we always have a horizontal tangent. Yeah? We can draw in some of those solutions. The slope fields for this problem means that you really do legitimately just like, okay, so if I want to draw in slope fields, let me just look at when x is 0. When x is 0, what is the slope, right? So if I think about different values that nicely here, this problem only depends on x, right? If I think of x and y prime minus x, if x is 0, what is y prime? Y prime is 1, right? So when x is 0, whenever I cross here, I cross with a slope of 1. That's a 45-degree angle. Does that make sense? Got that? Yeah? Well, what about when x is negative 1? Well, then y prime is 1 minus negative 1, so we got 2, right? 1 plus 1 is 2, yeah? So if I'm over here at negative 1, then what do my slopes look like? Well, the slopes are twice those slopes, right? So, yeah, does that make sense? Okay, and we'll do one more. What if I have x is 2, then 1 minus 2 is negative 1, right? And therefore, all the slopes here when x is 2, the vertical line when x is 2, the slope of the tangent line is always negative 1, right? So it's always that. Yeah? Okay. So we can keep going, right? This one is fairly nice, right? Because it has no y's in it. So that means, right, that for any x, it doesn't matter where you are in the xy plane, the slope for y is always the same. Now, as soon as you got y's involved, that's no longer going to be the case, right? Okay? So we can probably draw some nice solutions in here, right? We know over here we're increasing. We have to have these slopes. We are here. Well, I guess probably this is about. Okay, there's one. Yeah, there's another one. Yeah, there's another one. Solution. So this is where it's nice to have all those nice drawings in your book that are actually accurate, and you can see, so when I cross negative 1, the slope of the tangent line right there is 2. When I cross 0, the slope of this tangent line right here is 1, right? When I cross 1, the slope of the tangent line to the solution is 0. When I cross x equals 2, the slope of the tangent line to the solution is negative 1. Yeah? And so these guys are our upside down parabolas we might have expected from integrating that guy. Infinitely many solutions because we have our plus c, right? Okay? The plus c will act as a vertical shift here for these problems. And if we wanted to specify a specific initial condition, that would pick out one of these infinitely many solutions, right? And our theorem, right, let's look at our guy. Here's our f of x and y. Is this function continuous for all x? Absolutely, it's polynomial, right? Continuous for all x. What is the partial derivative of this with respect to y? 0, yeah, 0 is continuous. And so this ODE plus any initial condition is guaranteed to have a unique solution, at least within the range of the initial value. Yeah? Does that make sense? Okay? So before we go off and do some slightly more complicated ones, I'm going to stop the video now just to make sure that it all actually worked. We'll come back in and we'll pick up with this one and seeing what we could draw based on slope fields and utilizing calculus, right, to understand exactly what's happening and where as far as increasing and decreasing in concavity is concerned. I'm going to want you to be able to do that. And then we'll go on and do yet another example. So to try to avoid these getting too long, too quick, I'm going to stop this one, and you might want to try that one on your own before I come back and do it for you, right?